Hi everyone, welcome, live long and prosper. Hi, good morning. Yes, so we're about to finish chapter 7 on complexity theory. And our next chapter will be the final chapter 8, approximation algorithms. A new way of analyzing the performance of algorithms, not in terms of runtime or memory, but in terms of approximation ratio. So let's recall what we've learned so far. And here's the screen. Maybe we've seen several decision problems about graphs. We've talked about the Eulerian cycle problem and the Hamiltonian cycle problem, which superficially seem very similar, but for the Eulerian cycle problem, we were able to find a polynomial time algorithm. For the Hamiltonian cycle problem, we were able to show that it can be that it belongs to this class NP, that it is polynomial time verifiable, but we have not been able to find a polynomial time algorithm for this problem. Nor have we been able to prove that there is no polynomial time algorithm. Small change, small difference between both problems seems to make a huge difference in complexity, and I emphasize seems to make a difference because we cannot prove so. Next, we discussed the edge cover problem and the vertex cover problem. Again, two problems about graphs which superficially seem very similar. In the first case, we are supposed to find the smallest edge cover. In the second case, we're supposed to find the smallest vertex cover. Now, technically, both are optimization problems, minimization problems, but we have reformulated these problems as decision problems, namely not asking for a minimum size of an edge cover or vertex cover, but given an integer k, does there exist an edge cover? Does there exist a vertex cover of size at most k? These are decision problems, and we've been able to devise a polynomial time algorithm for the edge cover problem. This algorithm was based on or built on the Jack Edmonds algorithm for finding a maximum matching, which is a polynomial time algorithm. We have not been able to devise a polynomial time algorithm for the vertex cover problem, although it seems so very similar. Nor have we been able to prove that there is no polynomial time algorithm for the vertex cover problem. So again, here we're in kind of a limbo. We don't know whether the algorithm we have found is optimal or not. But that's precisely the point, one of the virtues of computer science. Either prove that the algorithm we have found and analyzed is optimal, or look for a better algorithm and then prove that optimal. Here we cannot achieve either, which is kind of annoying. Then we have looked at the click problem and the independent set problem. Again, both are decision problems in graph. Click asks to find for the largest click, the largest complete subgraph. Independent set asks to find the largest independent subgraph, the largest set of vertices which are pairwise not connected to each other, so that between any two of these vertices there is no edge. So this is not the opposite of the click problem. The opposite of the click problem is to find k vertices such that which do not form a click, and do not form a click means some of the vertices are not connected. For the independent set, all of the vertices must be non-connected. And again, we've been able to show that these decision problems belong to this class NP. They are polynomial time verifiable. And recall that this is proving that a problem belongs to this class NP. Our syntactic definition, we don't refer to non-deterministic polynomial time Turing machines in this lecture, so please also you refrain from referring to non-deterministic Turing machines in your homework solutions and final exam. So we take the perspective of NP in its syntactic definition, namely decision problems of the form given x. Here we are, given x. Does there exist a witness of polynomial length? A witness for x belonging to the set L. A witness such that the pair x, y can be verified, can be decided in polynomial time. And we've been able to reformulate all of the above problems in this form and thus prove that they do belong to NP. Reformulating means devising V, the verifier, polynomial time decidable verifier, and finding a notion, a meaning, a semantics of this witness of polynomial length. So to summarize, for some of these problems, we have been able to devise and analyze polynomial time algorithms. For others, we have not. The best we have achieved for these problems was to show that they are in this syntactic form of NP. And as I said, this is kind of a limbo. So how do we proceed from here? And fortunately, there's a way of comparing decision problems of unknown complexity. And this is a kind of extremely ingenious way of dealing with the situation. We don't know, but we are able to compare the complexity and thus arrive at this famous class of NP-complete problems that you probably have heard of. So how do we compare to the two decision problems? How do we compare their computability? How do we compare their computational complexity? A motivating example, we've reconsidered the two problems, click and independent set, and we've seen that there is kind of a relation between them. Namely, in this example, we've seen that the four red vertices form an independent set of size 4 vertices. The four red vertices are pairwise not connected. And in this example graph, we've seen that the same four vertices form a four click. They are pairwise connected. And the relation between these two graphs is that one graph is the complement of the other. One graph, when there's an edge present between any two vertices, then in the complement graph, that edge is absent, and vice versa. When an edge is absent, like here, the edge between these two vertices is absent, then in the complement graph, the edge is present. So this is the relation between these two kind of graphs. And the observation, our observation is that whenever there's an independent set of size k in this graph, then the complement graph has a clique of the same size k. And vice versa, if this graph has a clique of size k, like in the example, the four red vertices, then the original graph has an independent set of size k, namely the very same vertices. So that proceeding from a graph to its complement means proceeding from cliques to independent sets and taking the complement a second time, arriving at the original graph, back at the original graph, means translating independent sets of size k into cliques of size k. Now let's suppose that any of these two problems, let's say the click problem, admits a polynomial time solvable algorithm, an algorithm which solves the decision problem in polynomial time. Then we can convert that into an algorithm which also solves the independent set problem in polynomial time as follows. So our new algorithm for the independent set problem receives as input such a graph and an integer k, and our algorithm will form the complement of that graph. It will flip the presence and absence of edges, which is easy to do just in the adjacency matrices. Flip all bits, replace zeros with ones, and replace ones with zeros. That means every edge that was present before is now absent afterwards, and vice versa. And by our observation, this new complement graph has a clay click if and only if the original graph had an independent set of size k. And since we operate on the hypothesis that there is a polynomial time algorithm for the click problem, then we can thus solve the independent set problem by using that hypothetical algorithm. Let me say that again. If there is a polynomial time algorithm for the click problem, then we can combine that with a simple algorithm for inverting the graph, for computing the complement of the graph, for flipping edges between present and absent, and arrive at a polynomial time algorithm for the independent set problem. Why is that again a polynomial time algorithm? Because the flipping the edges only takes polynomial time, right? So there's a polynomial number of edges, at most quadratically many, and then feeding the resulting graph, the complement graph, to the hypothetical algorithm for the click problem. That's what we've just argued constitutes an algorithm, polynomial time algorithm, for the independent set problem. Which means that the independent set problem cannot be harder than the click problem. We don't know whether there is a polynomial time algorithm for click or not, but if there is, then there also is an algorithm for the independent set problem. We haven't been able to describe that algorithm completely, but we have kind of performed a meta-programming. We have taken the algorithm for the click problem and modified that to arrive at the polynomial time algorithm for the independent set problem. That's why I like to call this meta-programming, modifying hypothetical algorithms without knowing, without caring how they operate. We can still modify such a hypothetical algorithm. And the curve converse also holds. If we have a polynomial time algorithm for the independent set problem, then we can use the same meta-programming approach to convert that into a polynomial time algorithm for the click problem. Namely, take the algorithm for the independent set problem and prepend that algorithm with our simple algorithm that flips edges, because flipping edges converts independent set of size k into clicks of size k and vice versa. So that again, the independent set problem and the click problem have the same complexity. Neither of them is harder nor easier than the other, because any efficient algorithm for one can be converted using our meta-programming into a similarly efficient algorithm for the other, and vice versa. Which means that either both problems have a polynomial time solution or none. We don't know which one is the case, but we've already now observed an important structural property of this question. Either all or none of these problems admit a polynomial time solution. So although we don't know which one is the case, there's still significant insight gained by using complexity theory. Now let's generalize and formalize this notion, this approach of comparing the computational complexity of problems whose computational complexity absolutely we don't know. Namely, we consider the notion of a polynomial time reduction. This is a refinement of a notion which has been known for ages in, well, for decades in computability theory, namely reduction. So we consider two decision problems, both as subsets of finite binary strings, and we say that first decision problem K can be reduced to the second decision problem L in polynomial time if and only if there exists a total polynomial time computable function from all finite binary strings to finite binary strings with the following property. Whenever some finite binary string x belongs to the first problem, that means whenever we're supposed to give a positive answer for that input x, then the translated version, the image f of x, belongs to the other decision problem L, which means that for this we need to give a positive answer, and vice versa. So there's an equivalence here. And this captures, this formalizes our example about the click and independent set problem. Let's reconsider these two problems, and let's consider K, the first decision problem here, to be the click problem, and let's consider L, the second decision problem, to be the independent set problem. And we claim that these two problems indeed admit a polynomial time reduction, namely the graph complementing function is a polynomial time reduction. So what does it mean? It means we call that the graph complementing function is a function that, well, originally it operates on graphs and flips at presence and absent on edges. But since we're overall encode graphs, it is basically a mapping of finite binary strings, namely on encodings of graphs. And we've already verified that it has this central property. Whenever the click problem has, whenever the graph has a click of size k, then its complement graph has an independent set of size k, which means one direction of this implication, right? So x here stands for the binary encoding of the graph under consideration. And we have also the converse. Whenever the translated graph, the graph with edges flipped, has an independent set of size k, then the original graph has a click of size k. So that indeed our example above is an example illustration of the above below notion of a polynomial time reduction. So as a next step, let's record some properties of this polynomial time reduction. But first, let's draw a picture of this reduction. So here in this picture, the blue box represents the set of all finite binary strings, and the gray shape represents the set, a certain decision problem K, a subset of finite binary strings according to our definition. And we have the same here for another set L decision problem, only here we chose a different shape just to emphasize this, that this in general will be a different decision problems, and it's a subset of the finite binary strings again. And we consider function from the left to the right, from the first decision problem to the second, must be a total function. It doesn't need to be surjective, it doesn't need to be injective, but it must satisfy this equivalence here, which means that all points in the original decision problems must get mapped to points in the second decision problems, and all points which are outside of the decision problem, which suppose us to give a negative answer, are mapped to points which are outside of the second decision problems. Again, this function need not be injective, this function need not be surjective, but it must maintain the answers to the decision problem. True answers must be mapped to true answers, false answers must be mapped to false answers, which means element in the set must be mapped to elements in the set. Elements outside of the set must be mapped to elements outside of the set. And we've seen that complementing a graph satisfies this property when K is the clique problem and when L is the independent set problem. And the nice thing about this new notion, which generalizes the example we've just considered, is it has nice properties. First property is if the set, the decision problem L, somehow turns out to have a polynomial time solution, then we can use a polynomial time reduction to convert that into meta-programming, into a solution of the decision problem K, which is going to be again polynomial time algorithm. So that's a claim of lemma A. Let's prove that. Let's see how this works. So in order to prove claim A, we consider polynomial time algorithm for L, right? So hypothesis says L is polynomial time decidable. And now we use this meta-programming approach. We prepend this algorithm with a edge inverting algorithm. This algorithm has polynomial time, so it is a function, total function in this very sense. And so that whenever we have a polynomial time algorithm for L, then composing that, prepending that with a translation function f gives rise to a polynomial time algorithm for K. Why is this a polynomial time algorithm? Well, because the two phases that comprise our algorithm are both polynomial time computable. The first phase takes a given argument x and translates that into f of x, and according to this equivalence, this translation maintains truth. So whenever the original problem, the original instance, the original input had a positive answer, then so does the translated problem for the second decision problem. So what remains is now to feed the result of the translation into the hypothetical algorithm, polynomial time algorithm for L. And important observation, the composition of two polynomial time decidable problems is again a polynomial time decidable problem. There's a subtlety involved here that I'd like to point out, namely, so we're given to show that these problems are closed under composition. Consider an input, some input x, and according to our meta-programming, we first convert that x into f of x in polynomial time. And the observation is that f of x now has polynomial length. Why is that so? So input is a finite binary string x of some length, let's call it n. And the claim is that after the translation, which we call here f, the length f of x is at most polynomial in the original length. Why is that so? Well, because according to our definition, this f is polynomial time computable, and in polynomial time, every single bit output charges or costs one time step, right? If we output a bit, that costs one step according to our measure of computational complexity. So that means within polynomial time, we can output at most a polynomial number of bits. Therefore, whenever x belongs to k, admits a polynomial time solution, then f of x can be computed in polynomial time, and next output or fed into the hypothetical algorithm that decides L. So that concludes the proof of item A. And regarding item B says that this new notion of polynomial time reduction is closed under composition. Let me say it again more formally. When L is polynomial time reducible to L prime, and when L prime is polynomial time reducible to L double prime, then there is a polynomial time reduction directly from L to L double prime. So that's a claim of item B of this lemma. Let's prove this item B. And again, so we consider some input x for the first decision problem L and a polynomial time reduction, a function that converts this x into some y as abbreviation for f of x. And as we've just observed, in a polynomial number of steps, an algorithm can output only a polynomial number of bits, which means that the output length of this translation must be at most polynomial. In what? Polynomial in the input length. Okay. And in particular, the output length is at most polynomially longer than the input length. It can be that it is longer, right? So the translation is allowed to extend the length, but since it's a polynomial time for translation, it can extend the length at most polynomially. Now we feed that output, let's call it y, of the first translation into the second translation from L prime to L double prime, which means the same thing. We put this into the translation, which is supposed to run in polynomial time, and therefore the length of the input gets longer by at most a polynomial factor, which is in total still a polynomial. And therefore, the total reduction directly from L to L double prime can be computed just as the composition of the two reductions, the first from L to L prime and the second from L prime to L double prime. So composition of polynomial time function is again polynomial time computable, and therefore it holds this property of polynomial time reduction that they're closed under composition. Let's now consider two decision or rather approximation problems. The first is the traveling salesperson problem. The traveling salesperson, imagine you're a traveling salesperson, you live in the United States and you're supposed to tour all the major cities in the United States and try to sell your product. Yeah, you're a traveling salesperson after all. And the goal is to find a tour that is a cycle that starts in some city, let's say New York, and ends in the same city, and on the way we'll have visited every single city precisely once. Okay, let me say it again. Traveling salesperson problem in a graph theoretic framework is the following. Given an undirected graph, find a tour, find a cycle that visits each vertex precisely once. That's basically the same as Hamiltonian cycle problem, but the additional condition here is that among all graphs, among all tools that satisfy this property, our tour should be smallest, have the least total length. This is the traveling salesperson problem. This is an optimization problem, a minimization problem. Find a shortest tour. And we're going to reformulate that as a decision problem using the method we've already mentioned. Namely, instead of giving a graph and asking for the least tour, we're given a graph and we're given an integer k and ask whether there exists a tour of length at most k. So that's basically the same as the Hamiltonian cycle problem, except that now here we're interested in the length. So if the graph has a Hamiltonian cycle, then the question whether it has one is trivially true, but then we're asking for the shortest one of shortest total length. This is the traveling salesperson problem. Here's a formalization of the traveling salesperson problem as encodings of pairs, graph and integer. So in this setting, the graph can be weighted, which means it can have some edge weights. So not all edges are created equal, but some are longer, some are more expensive, and some are cheaper, some are less expensive. And so the goal is to find shortest tour with respect to these edge weights, that is a cycle. And the question is whether there exists a cycle of length at most k, thus having converted the minimization problem into decision problem. And as I said, this is pretty much similar to the Hamiltonian cycle problem, except that in Hamiltonian cycle, we're just asking whether there exists a graph. And the first observation and application of our reduction notion is that indeed Hamiltonian cycle admits can be reduced to the traveling salesperson problem. It is at most as difficult or different whenever we have a polynomial time algorithm for traveling salesperson, then this can be converted into a polynomial time algorithm for Hamiltonian cycle at most polynomial slowdown, namely the slowdown that is incurred by the translation function f here. Now, how does that reduction work in this specific example? So let's practice that. So we're given a graph and an integer k, right? And we're asked to find out whether the graph has a Hamiltonian cycle. No, sorry, we are not given an integer k, just a graph, and we're supposed to answer whether this graph has a Hamiltonian cycle or not. And to this end, we use the hypothetical algorithm for traveling salesperson as follows. We're going to add edge weights to our original graph. So we're supposed to answer whether the graph has a Hamiltonian cycle, which means a tour that visits every city precisely once. And we're going to, this is about non-weighted graphs, but in our reduction, we're going to add edges, edge weights. Then we were going to add edge weight 1 whenever there's an edge present in the original graph. Intuition is that traversing this edge is going to be cheap. And we're going to add an edge of large weight whenever there's no edge present in the original graph. So let's consider two vertices in the original graph. If there are no edge between these two vertices, then our translation will add an edge, but an expensive edge, an edge of weight which is much larger than the weight of any other edge occurring into the graph. More specifically, we can choose the weight to be n, the number of vertices. And observe that this is a non-negative integer weight. So that whenever the original graph had a Hamiltonian cycle means just visiting all edges, and the total number of edges in this cycle visiting all vertices, and the no total number of vertices in this graph is of course n, right? So then that means when there is a Hamiltonian cycle, then there exists a Hamiltonian cycle of length at most n, and in our translation that gives rise to a tour of length at most n, because we've assigned 1 to all the edges that were present in the original graph. That proves one direction of this equivalence. For the converse direction, let's suppose that our translated graph has a Hamiltonian has a cycle of length at most k. If it has a cycle of length at most k, well, we'll choose k equal n. If it has a cycle of length at most n or k, then that means that our graph, that our cycle only uses the cheap edges from our translation, the edges that have cost at most 1. And these, by definition, are the edges that are present in the original graph, and therefore this cheap tour corresponds or gives rise to a Hamiltonian cycle, a cycle that only uses the edges that are present. So to summarize, we've just seen our second example of a polynomial time reduction from Hamiltonian cycle to traveling salesperson problem, and intuitively it was clear that asking whether a graph has a Hamiltonian cycle should be easier than asking whether a given graph has a cycle of the length at most k. If we formalize that in terms of a polynomial time reduction that converts the first graph into the second graph together with an integer k. In the second problem, observe that k is part of the input, so we can and we must take that into account when constructing and analyzing the reduction. Good, so this concludes our discussion of the traveling salesperson problem as a decision problem, and we've seen that traveling salesperson problem does not have a polynomial time algorithm. Why not? Why is that? Because if it had a polynomial time algorithm, that would be more difficult than the Hamiltonian cycle problem according to our reduction. But we have seen before that we don't know any polynomial time algorithm for a Hamiltonian circle. So there doesn't seem to be a polynomial time algorithm for traveling salesperson. Other problem we're considering is the knapsack problem. Again, this is an optimization problem. Actually, it's two optimization problems. So what's the motivation? What's the idea? Let's suppose it's Christmas time and Santa Claus is supposed to bring presents, and these presents must fit into the knapsack that gives rise to the name of the problem. So formally, the input to the knapsack problem is the number n of packets, values of the packets. You can imagine each value to be a number of US dollars, and weights of the packets. And intuitively, knapsack can carry only packets up to a certain weight. So that we impose here a weight bound and ask whether there exists a subset of the packets as large as possible of as high a value as possible that that honors the weight bound. And formally, the question is, does there exist a subset of 1 to n, that's the indices of the packets, which maximizes the total value, the sum of all packets that are present in our knapsack, add up their values, subject to the weight bound, namely the total number of packets, their weights must be less or equal to W, otherwise the knapsack breaks. So that's knapsack as a maximization problem. Maximize the values of choose a subset of the edges of the packets that maximizes the values while respecting the weight bound. A different way of formalizing knapsack is as a minimization problem. Namely, here the goal is to minimize the weight of the knapsack. So previously the goal was to respect the weight bound, and here our goal is to keep the knapsack as light as possible, but now there's a condition, a constraint that the value must not be too cheap. This is like at Christmas when you need to give a gift, an expensive gift to your professor. No, just kidding. So the value bound means that the total value of all gifts in the knapsack must be at least capital V, and the weight should be as small as possible in the second conception of knapsack. And these are two different things. It's not the same, mind you. And again, this is a hard decision problem. This is supposed to be a decision problem. So here it's formulated as minimization and as maximization problem, but we can reformulate this as decision problems, namely given a weight bound and given a value bound, is it possible to simultaneously satisfy both bounds using a subset? And this is another hard problem. It is at least as hard as the Hamiltonian cycle problem, at least as hard as the traveling salesperson problem. Therefore, there are polynomial time reductions from the other problems. So we cannot hope for an efficient algorithm solving that problem exactly. And this motivates our study in the next and final chapter of approximation algorithms. So to summarize, we've talked about the complexity classes P and NP of decision problems, where NP in this lecture is defined as polynomial time verifiable problem of this special syntactic form not involving polynomial time Turing machine. We've discussed several decision problems about graphs. Question whether a given graph has a Eulerian cycle. Question whether a given graph has a Hamiltonian cycle. Question whether a given graph has an edge cover of size at most k. Question whether the given graph has a vertex of size at most k. Question whether the given graph has a clique, a total subgraph of size at least k. Question whether a given graph has an independent set of size at least k. And for some of these problems, we've been able to find polynomial time algorithms, and for others, we haven't. And our goal to determine the computational complexity of those problems for which we haven't found one led us to the notion of a polynomial time reduction as a means to formally compare these decision problems, although we want to compare the computational complexity without knowing the computational complexity. And this was achieved using this notion of a polynomial time reduction. And then we've looked at two decision problems that arise from optimization problems. Traveling salesperson problem. Goal is to minimize the length of the tour when selling things to customers in the United States. And the knapsack problem, which can be considered as both a maximization and as a minimization problem, but there's a decision person problem is the same in both cases, given a selection of packets and given a weight and given a value bound. Is it possible to find a subset of the packets that exceeds the weight, the value bound, while maintaining the weight bound? Good. That's all for this chapter, and we now take a short break before starting with chapter 8 about approximation problems.